The first colligative property that we're going to be looking at is vapor pressure lowering. Colligative property was explained in the video for last week, which is basically it is a property that depends on the concentration of the solution of the solvent, concentration of the solution, not the identity of the solute. So what I have shown here is I have two flasks, okay, and in the flask on the left it's pure water, okay, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 water molecules that are at a constant vapor pressure. So this has reached equilibrium and the vapor pressure is constant. By adding this, making this a solution, by adding these purple balls to it, whatever the molecules they represent, all of a sudden the number of water vapor in the gas phase above here is less. So I have 1, 2, 3, 4, 5, 6, 7, 8. So in the one where I have multiple, I have 8 water in the gas phase, whereas over here I said it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So by adding a solute to and making a solution, I reduce the water pressure, the vapor pressure of water, by 4 waters in this particular example. So Réalt's law basically states the relationship here. It says the partial pressure of the solvent, which is PA. So A is solvent, equals the vapor pressure of the pure solvent, which pure is symbolized, this means pure, this little degree symbol here, times the mole fraction of the solvent. So again, A denotes, the subscript A denotes the solvent in this example. And so basically that definition is this formula. The vapor pressure of the solution of A is equal to the pure vapor pressure times the mole fraction of the solvent. And this only holds true for dilute solutions. So over here, when we do a graph of the mole fraction of the solvent versus the vapor pressure of the solvent, Réalt's law says that it should hold true no matter what. That's the linear line there, okay? In reality, though, it follows the red line, okay? And so the red line and the blue line only overlap from about here, which is about approximately 0.9 mole fraction of the solvent, all the way to pure solvent, which is up here, okay? So we're only going to be working with solutions that have a mole fraction of the solvent greater than 0.9. One more thing before we go to the next slide is if A is solvent, B is the solute in the equation. So for dilute solutions, it can also be said that the change in pressure, so this means change in pressure, is again the pure vapor pressure of the solvent, but this time it's the mole fraction of the solute here. Okay, so A is solvent, B is solute. And the way to kind of remember this is, even though this formula is given to you, since it's the vapor pressure of the solvent that we're talking about, so A has to be my solvent. And so when it's not A and it's B, then that means it has to be the solute. So here's an example here. It says the solution is prepared by dissolving 396 grams of sucrose in 624 grams of water. What's the vapor pressure of the solution at 30 degrees? And the vapor pressure of water, it should say pure water, is 31.8 millimeters of mercury at 30 degrees. And I went on ahead and gave you the molar mass of this. I've noticed that some people are having a hard time here. This was gotten by the fact that I took 12, because there's 12 atoms here, times the 12.01, plus 22 times the 1.01, for that's hydrogen, plus 11 times the 16 for the oxygen, and that's going to equal the 342.34. So when the molar mass is just the sum of each of the number of atoms times the atomic weight for that. So I have a mass of equal to 396 grams, and that's of C12H22O11. I have a mass that's 624 grams, and that's water. It wants to know what is the vapor pressure of water, because that's my solvent. I have a temperature of 30 degrees C, and the pure pressure of water is given as 31.8 millimeters of mercury. Temperature still 30 degrees, okay? So it has to give me a temperature because the vapor pressure is temperature dependent, but I'm not actually going to use it in my formula, so I'm going to scratch that out. So the formula that I'm going to use is the vapor pressure of water is equal to the vapor pressure of pure water times the mole fraction of pure water. So I'm trying to find this, I'm given this, but I need to find this before I can plug into the equation. So the mole fraction of water, this is why we had to do this first, it's going to be the moles of water over the moles of solution, which is moles of water, plus moles of the C12H22O11. That's the sum of those two together. So I have to find the moles of water. In order to do that, I need the molar mass of water. Again, it's 2 times the 1.01 for hydrogen and 16 for oxygen, so it's 18.02 grams per mole. So the moles of water is equal to the 624 grams divided by 18.02, and I got 34.63, and that was 4, just like this was a 4. It kind of wrapped around. And this is moles of water. So that's that and that. I need moles of my sucrose, so moles of C12H22O11 is the 396 divided by the molar mass of that, which was 342.34. And that gave me 1.157. Okay, so now I'm ready to find the mole fraction. So the mole fraction of water is the 34.63 divided by the sum of 34.63 plus the 1.157. That's a 1 there. Okay. And that gave me 0.9677. There's no units for that one. Okay, and now that I have the mole fraction, I'm ready to substitute back into this equation. So my pressure of water for the solution is my pure pressure, which was given as 31.8 millimeters of mercury, times my mole fraction, which doesn't have a unit, 0.9677. And when I multiply those two together, I get 30.8, and the unit's going to be whatever unit of pressure they gave me, which is millimeters of mercury for this problem. Okay. A second example of this problem is that at 25 degrees, so I have a temperature of 25 degrees. Again, it has to give you temperature because vapor pressure is temperature dependent. It tells me of pure benzene, so P naught of benzene, is 93.9 torr, which is another pressure unit. It says a non-volatile solvent is dissolved in benzene, and the vapor pressure of benzene, this should be solute, the vapor pressure of benzene is lowered to, so the pressure of benzene solution is 91.5 torr. They want to know what the mole fraction of the solute is. And they want to know what the mole fraction of the benzene is. So there's two different ways that you can do this problem. Okay, I can use the pressure of benzene is equal to the pure pressure of benzene times the mole fraction of benzene Okay, and so I'm going to use the solution was 91.5. The pure was 93.9 times the mole fraction of benzene. So I'm going to divide both sides by 93.5, or 93.9, sorry, 91.5 divided by 93.9 is the mole fraction of benzene. So the mole fraction of benzene is 0.974. Again, there's no units for that. And because there's only two components to this, the mole fraction of my solute can be gotten by taking 1 minus the 0.974. And I get 0.0256. Again, no units there. So that's way number 1. Way number 2, which I'll do in blue. So this is a completely independent method. It doesn't matter which one. I can use the change in pressure. It's still the pure pressure of benzene times the mole fraction of benzene. The change in pressure is P naught minus P. So it's going to be the 93.9 minus 91.5. And that gives me 2.4. And that's torr. So then I just substitute this in. So I have 2.4 is 93.9. This must be a 9. Times the mole fraction of, oops, this is not solute. Sorry. I mean, not benzene, this is solute. So I divide both sides by the 93.9, so 2.4 divided by 93.9 gives me the mole fraction of solute. So the mole fraction of solute is equal to the 0.0256, same number as I got over here, and then the mole fraction of benzene can be found as 1 minus the 0.0256, which gives me the 0.974, and there's no units there. Okay, so that's using that's the first of the colligative properties using mole fraction, and those are the two example problems.